Check this out. We've got something really fun today. This is so amazing. Oh man, again? Let's warm up by finding the reciprocal of each one of these expressions. When we find the reciprocal, we take the denominator and move it into the numerator, and the numerator and move it into the denominator. So the reciprocal of 3 over 5 is 5 over 3. What if it doesn't have a denominator? By default, that denominator would be 1. And so the reciprocal of 5 is 1 over 5. Careful with something like this. We have to take the reciprocal of the whole thing together, and so as a mixed fraction, that's going to be difficult. So let's change this one first. So this would be equivalent to 16 over 5. And now we can easily take the reciprocal of this and get 5 over 16. For this one, take the reciprocal of the whole expression, not the individual terms. So the reciprocal would be 1 over 5 plus x. And that's different than taking the reciprocal of the individual terms and getting 1 over 5 plus 1 over x. Do not do it like that. 7.4, reciprocal functions. We saw how we can take the reciprocal of numbers or expressions. Now we're going to take the reciprocal of a function. So if we had something like y equals f of x, then its reciprocal function, we're going to create a new function, 1 over f of x. Now since f of x is now in the denominator, it cannot equal 0. So we'll have to watch out for that. If xy is a point on the graph of f of x, then x 1 over y is a point on the reciprocal graph. So for example, let's get a point here. Let's say the point 2, 2 is on the point f of x. Then the reciprocal point would be 2, 1/2. Notice nothing changed for the x value of the coordinate, just the y value that we're taking the reciprocal of. We're just taking the reciprocal of f of x here, and f of x is our y value. And this also works the other way around. If we had a point 2, 1/2 on our graph, the point on the reciprocal graph would be 2, 2. Let's sketch our most basic reciprocal function, 1 over x. That would be the reciprocal of x. So I've already done y equals x here. I've drawn it on the graph, and I've also filled in the table of values just because y equals x, they share all the y value is the x value here already. Let's do y equals 1 over x. So that would be negative 1 over 5. Or you could put negative 0.2 if you prefer. Reciprocal negative 1 over 2. Reciprocal of negative 1 is negative 1. Reciprocal of negative 0.5 is negative 2. Reciprocal of negative 0.2 is negative 5. And reciprocal of negative 0.1 is negative 10. The reciprocal of 0 is undefined because that's the point where we got 1 over 0, we're trying to divide by 0, and that cannot happen. And then we've got the positive values here. Reciprocal of this is just 10, reciprocal of this 5, reciprocal of this 2, reciprocal of 1 is just 1, reciprocal 1/2, and reciprocal 1 over 5. Let's try to put these, plot these points on the graph and connect them. The reciprocal graph is drawn in blue, and it looks like there might be two graphs here, this one here and this one here, but really it's two parts of the same graph. So when I plot these on here, this one goes down, down, down. It's going to continue on, get closer and closer to negative infinity. And this one, all of a sudden, after this undefined point, it is very, very large, so it would be getting close to positive infinity then. So these are two parts of the same graph. So will it ever cross the x-axis? That would be no. You can see that from the graph. It does get pretty close. If you put it in your graphing calculator, it looks like it does touch. But it doesn't actually touch, no matter how large a number you have here. If you take the reciprocal, you're always going to get that 1 in the numerator, not 0. So to get 0 in the numerator, you'd have to take the reciprocal of something that was undefined, and that can't happen. So no, this never touches. So make sure you exaggerate the space in between the x-axis and your graph, and on the same point in between the graph and the y-axis as well. So it doesn't look like it ever touches. What happens on the graph when we try to divide by 0? Well, it shoots downwards and comes from up very high, positive infinity. So we indicate this by drawing an asymptote. So this vertical line here, drawn in dotted green, is our vertical asymptote. Its equation is x equals 0. This horizontal line here is our horizontal asymptote, and its equation is y equals 0. And last, there are some points that do not change. We will call these points invariant points, as in they do not vary. So invariant points, they're actually at 1, 1, and -1, -1. Let's mark those on the graph. So these 2 points right here, this point here and this point here, are invariant. Normally asymptotes are defined as a line that the graph approaches but never crosses, but we know that horizontal asymptotes can be crossed or can be touched. So a little bit of a bad definition there that most people use. Vertical asymptotes, this is true. It can never cross it. So the vertical asymptotes occur at the non-permissible values of the reciprocal function, which were, very important, the x-intercepts of the original function. Horizontal asymptotes. For reciprocal functions, the horizontal asymptote will always be at y equals 0 or be the x-axis. So very easy to remember. Take a few moments, see if you can fill in this table. When you're done, continue the video. Y equals x has a domain of all real numbers, and 1 over x, all real numbers except it cannot equal 0, because then we'd be trying to divide by 0. The range, well, the range for this one would be all real numbers for the y's, and the range for this would be all the real numbers except it can't equal 0. So there it is. Okay, the end behavior. That's what's the graph doing at the ends, if it could have ends. So in quadrant 2 or 3 on sort of our left quadrants, what's the graph doing? So let's see, y equals x. That would be when x is less than 0, and the absolute value of x is very large, so it may be approaching negative infinity. Then y is less than 0, and the absolute value of y is very large. Yeah, that sounds like this first one here. Okay, if x is less than 0 and the absolute value of x is very large, then y is less than 0 and y is close to 0. That sounds like the reciprocal graph, close to 0. And in quadrant 1 and 4, so on the right quadrants of our Cartesian plane, what's the graph doing? That would be when x is greater than 0, absolute value is very large, and y is greater than 0, and the absolute value of y is very large. So that would be that one. And this one is close to 0, so that would be this one. Value at x equals 0, well then y equals 0. This one here, undefined. Invariant points. Well, these work together. I'm just going to put it in the middle. Really invariant, you can't be invariant with yourself, so we'll say between these two graphs, they have invariant points of -1, -1, and 1, 1. Horizontal asymptote, none. And vertical asymptote, none as well. That's just a straight linear line, y equals x. Horizontal asymptote for this one, y equals 0. And vertical asymptote, not that, it would be at x equals 0. And the rest of these were just here to mix you up. Steps for graphing reciprocals. You may want to sketch the graph of y equals f of x. If it is not given, this is optional. And if you do it, make sure to label it. So don't just have two unlabeled graphs in your sketch. Plot the invariant points. They are located whenever y equals 1 and whenever y equals -1. Because when we take the reciprocal of those, they're the same. Draw the asymptotes, and then this is a good key how to draw it. Look at the graph of f of x. If it is increasing, then the reciprocal is going to be decreasing. And if f of x is decreasing, then the reciprocal will be increasing. Let's try this out with sketching the graph of 1 over 3x plus 9. We have the graph y equals 3x plus 9. There's the y-intercept of 9 and it has a slope of 3. So first step, let's mark our invariant points on the graph. So they happen whenever y equals 1. So we just follow this y equals 1 along, and when we hit the function, that's going to be an invariant point, and that's going to be a point on the reciprocal graph. There's no more. Add y equals 1. Y equals -1 along here is right here. So this also gives us an invariant point that's going to be on our reciprocal graph. Next, let's do the asymptotes. So the vertical asymptote happens when there was an x-intercept. So this is going to be our vertical asymptote. And for reciprocal graphs, our horizontal asymptote is always at y equals 0. So right along here. And now we're set up to draw the reciprocal graph. Now it may seem kind of obvious. We need to snuggle up next to our asymptote here, pass through our invariant point, and then snuggle up next to our asymptote here. But let's say we were looking at the first function here. It's increasing, and that means that it's decreasing here. So we know it goes like this. It's going like this, and then decreasing a little bit, and then decreasing a lot. Whoa. And it's supposed to be smooth, but and make sure you exaggerate that space. So don't let it look like it's going to touch there. So that would be the first part. We know it's not up here because see this would be increasing, so it would be going up. So that wouldn't work. And it doesn't pass through our invariant point anyways. This one here, the original is increasing, so that means our reciprocal needs to be decreasing, snuggling up next to our vertical asymptote, and then our horizontal asymptote, passing through that invariant point there, and off we go. So there's the graph of the reciprocal, y equals 1 over 3x plus 9. The equation of our horizontal asymptote, that would be y equals 0. The equation of our vertical asymptote in this one, that would be x equals -3. If we needed the invariant points, we could find that point right there, invariant point, by solving the equation 1 equals 3x plus 9. Or 1 equals 1 over 3x plus 9. They both give us the same answer, so just pick the easiest one to solve. So -8 on both sides, and then divide by 3 on both sides, we get x equals -8 over 3. So this invariant point right here is at -8 over 3 and 1. Using the same process except changing this to -1, we could find the coordinates of this other invariant point here. If we wanted to use a calculator to graph these, we could just type this into y1, make sure to put brackets around our denominator, get a table of values, and we could make a pretty good sketch of it. Graphing without a calculator, let's do this. We already have the original function here, 1 over 7 times x minus 1, graphed. So let's mark on our invariant points and our asymptotes, and then sketch that reciprocal graph there. So the invariant points happens when y equals 1, so I just follow it along, and it equals 1 right there, so that's going to be a point on our reciprocal graph. And when y equals negative 1, so that will be a point there on our reciprocal graph. Next we look for our x-intercept. That will be the vertical asymptote of our reciprocal graph, and y equals 0 is the horizontal asymptote here of our reciprocal graph. Now we're ready to sketch our reciprocal graph. It would probably look like this because it needs to snuggle up next to the asymptote, pass through that invariant point, and then snuggle up next to the asymptote here, and do the same thing here as well. Now remember, we can also look at this graph is increasing, and so this graph, the reciprocal graph, needs to do the opposite. It needs to decrease. So it can't do this up here because that would be increasing as well. So it's down here, and something like that. And we'll do the same here. This one is still increasing, so this one needs to decrease. So coming down here, and of course it needs to pass through our invariant point, so that would make sense. It's going to hit that point there. And I'm not really doing this too carefully. I don't know exactly what points it's crossing in here. I'm just making a sketch of it. So for this, that's good enough. This asymptote would be y equals 0. This vertical asymptote would be x equals 7. And this graph right here is our y equals 1 over 7x minus 1. What's this? We've got the reciprocal of a quadratic. And we didn't even sketch the quadratic yet, so let's get on that. To sketch this, we probably would like to find the x-intercepts. So if we factor this, we've got x minus 3 and x plus 1. That means our x-intercepts would be at negative 1 and positive 3. So I'll mark those on the graph here. Our vertex should be halfway in between those two, so that would be at x equals 1. And let's just find the y value of our vertex. So I'll plug in 1 into this equation, and looks like I get 1 minus 2 minus 3 is minus 4. So the vertex is at 1, negative 4. Let's mark that on the graph as well. There. Could mark some other points on here. Okay, now we can draw our quadratic. Whoa, okay. And I don't really care, well, it's pretty bad. I don't really care what's happening up here at the top. I'm only using this to sketch my reciprocal graph, so I don't really need this one perfect. But this is y equals x squared minus 2x minus 3. Okay, that's not what we want to graph. We want to graph the reciprocal of that. So let's draw on our invariant points, where they happen whenever y equals 1. I follow y equals 1 across, and there's an invariant point. And in this case, there's another invariant point there. Let's do y equals negative 1, follow it along, and there's an invariant point, and there's an invariant point too. So this one has 4 invariant points. Let's do our asymptotes. So our horizontal asymptote is always at y equals 0. And our vertical asymptote is where we had x-intercepts. In this case, we have them right here at x equals negative 1, and also at x equals 3. So we're going to have 3 asymptotes in this question. Now we're ready to sketch the reciprocal graph here. So we know it's not down here. See that? Because this is decreasing and there's no invariant points here. So it's got to be, this graph is decreasing, so it's got to be increasing. So it's got to be over here, hit that invariant point, whoa, and then don't hit the asymptote, something like that. We have to exaggerate the distance between the graph and the asymptote. This one here, watch this, it's decreasing up until the vertex. So that means our reciprocal needs to increase. So like this, increase, increase, pass through that invariant point. And the reciprocal of -4 is -1/4. So I could actually find that. That would be a point on our reciprocal graph, so I'm going to hit that. Now my graph starts to increase, so my reciprocal graph will start to decrease. And that makes sense because I want to pass through this other invariant point here. And then head down, snuggling close to my vertical asymptote. And then the graph is increasing in this one, so my reciprocal graph needs to be decreasing, and it also needs to pass through this invariant point there. And there we go. So these three blue pieces are part of the same graph, but they're broken up by the asymptotes. So this is y equals 1 over x squared minus 2x minus 3. Let's do the domain and the range for this reciprocal graph here. So the domain is, we'll do it in set builder notation. X is such that x cannot equal -1 and 3. And it's also all the other real numbers. The range is y is such that y cannot equal 0, because that's a horizontal asymptote, but it also doesn't equal anything in between 0 and this -1/4 here. We'll say y is less than or equal to -1/4, and y is greater than 0. And it can be all the real numbers as well. Let's try to find the invariant point, since I think that would be a bit difficult. So let's say where y equals 1. So we'll say finding invariant, so you know what we were doing here. And we've got y equals 1, so we'll set our equation. Remember, either equation will work, but we'll just use the simplest one, this parabola drawn in green here. -1 on both sides gives us x squared minus 2x minus 4. Now I'd like to solve this, but it doesn't look like I can factor it, so I guess I'm stuck with my quadratic equation. X is equal to -b plus or minus the square root b squared minus 4ac all over 2a. And then we're just going to simplify that, so we've got 2 plus or minus root 20 over 2. We can get a perfect square out of there. That would be 4. Bring it out. The square root of 4 is 2. Now there's 2's everywhere, so I guess I'll show that step there. 2 plus or minus 2 root 5 all over 2. Divide this term by 2 and divide this term by 2. We get 1 plus or minus root 5. So it looks like our invariant points, the two positive ones would be 1 plus root 5 and 1. And 1 minus root 5 and 1. And then we could do the same thing for when y equals -1 using the same process. But I'll leave that one for you to do. What if we're given the graph of the reciprocal and we want to find the original linear line, f of x? So in this case, there's some things that we know. We know that this point right here was the x-intercept of f of x. So I'm going to write that we know that this point here, -1, 0, is the x-intercept of f of x. Next thing we know is we have this point here. This is not an invariant point. It's not at y equals 1 or y equals -1. So it's not an invariant point. But we do know that the reciprocal of this y value here is on the graph of f of x. So the point on f of x is -2, and the reciprocal of this is -4. So this point here, -2, -4. So we know -2, -4 is also on f of x. Now we have 2 points. Now we can find the slope. So let's say m is equal to -4 minus 0 over -2 minus -1. So this would be -4, and this would be -1, which gives us a slope of 4. And now that we have a slope, we have a point. Let's use slope point form. As a reminder, that would be y minus y1 is equal to mx minus x1, where x and y are our variables, and y1 and x1 are the y and the x values of a point that we know. Let's use this point here, -1, 0. So y minus 0 is equal to 4, the slope we calculated here, x minus -1. Then we'll just tidy this up, and we'll also call it f of x, because in the original question here it said f of x. So I'll just change y to f of x. We don't need the -0, and we could write 4x plus 1. And then if we wanted it in slope y-intercept form instead, 4x plus 4. So either one of those would be great for our original f of x function. Now we want to sketch it. It has a slope of 4 and a y-intercept of 4. There's a y-intercept of 4 and a slope of 4. We'd just like to sketch this linear line. And we know it's linear because there's only one x-intercept here. Something like that. There's only one x-intercept, and they're going different ways. So this goes down, 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 down. And this piece also is going down, 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 down. So we know that the reciprocal graph would be going up, up, up the whole time. Match each graph with the graph of its reciprocal. So if the first one is linear, it's going up the whole time, and it has an x-intercept of 3. For its reciprocal, that means we need a vertical asymptote at x equals 3. Oh, there's 2 of them doing that. But we need one that goes down, down the whole time. So we need this one. It goes down here, and then it starts up here and goes down here, if it could start. So this one would be graph 1. Let's try the next one. This one also has an x-intercept of 3, but it's going down first, and then after the vertical asymptote, it's going to go, it's going up here, so it needs to go down in the reciprocal. So that would be this graph right here. Vertical asymptote at 3, going up and then down. So you can see the difference between this one's a linear and this one's a quadratic. They both only had one x-intercept. You see the quadratic has 2 different directions here, and the linear just has one direction. It's going down the whole way. And this one, of course, would be our last graph here. We've got 2 x-intercepts, -2 and +2. So we've got 2 vertical asymptotes, -2 and +2. Here's a graph of a reciprocal function, 1 over f of x. And we want to find the equation of f of x and its domain and range. There's a couple things we can see right from this graph here, and that is these were the x-intercepts of f of x. So let's make a note of that. They happen at -3 and +1. The other thing we can tell right away is the vertex. That'll be halfway in between, so 2 units over from the x-intercepts. That'll be the vertex. So the vertex of f of x would have been at -1, and the reciprocal of this is -8. Now we can make the function f of x using this information. We can do it in 2 different ways, using the x-intercepts, or we can use the vertex. And Let's see how we might do that. So first we'll do using the x-intercepts, which would be factored form. So our f of x would be in this form, f of x equals a, some stretch a, and then x minus 1 and x plus 3 to give us the x-intercepts of -3 and +1. Now we just need to find a, and we can use the vertex point to find this. That would be -8 is equal to a, -1, -1, -1 plus 3. And now just do some algebra, sort this out here. -8 equals a, -2 plus 2, so this is -4. Divide both sides by -4, and we get that a is equal to 2. So that means that our equation for f of x is 2, x minus 1, x plus 3. Let's do it using the vertex. And this time we're going to be doing it in vertex form. So we still have the stretch a, and this time we're going to use the vertex. It was at -1 and 8, so that's x plus 1 squared minus 8. Now we need a point. We can't use the vertex like we did here. We need some other point. So let's use the x-intercept 1, 0. This one here. We'll put that in here. So you got 0 equals a, 1 plus 1 squared minus 8. This would be 2. 2 squared is 4. So 4a minus 8 equals 0. Add 8 and divide by 4. A equals 2. Of course, it's the same a value as this one. And putting it together, we would get 2 x plus 1 squared minus 8. So there's our f of x in vertex form, and there's the f of x in factored form. And for our domain, we have all real numbers in interval notation, -infinity to +infinity. The range, our smallest range value is -8, so y is greater than or equal to -8. This was part of RF11, Graph and Analyze Reciprocal Functions, and we're just doing reciprocal of linear and quadratic. There's some questions. Try them out to see if you know what you're doing.